Can you hear me? All right. So, um, yeah, as she just said, I'm gonna tell you why you, as a Python developer, should learn Rust. Um, but before I get too much into that, I want to give you a little background about my background. So, I'm a software engineer at Sentry, which, for anyone who doesn't know, it's an error and application monitoring product. I've been working there for 2 years. And when I started out, I was working only on the Python SDK. Um, but then later, I ended up learning Rust so that I could um, take over maintenance of Sentry CLI, which is a command line utility written in Rust. And well, I really enjoyed that experience of learning Rust. And nowadays, I really enjoy writing Rust. And I basically want to share insights from my experience being a Python developer who learned Rust and basically tell you about some of my favorite features in Rust and why I think you should learn it. So yeah, this is kind of an overview of what I'm all want to talk about today. And the first thing I want to do is basically do kind of a high level overview of the difference between Rust and Python. And so I think one of the main differences between Rust and Python, of course, Rust is a compiled language and Python is an interpreted language. And Rust has this emphasis on safety and reliability, which means that a lot of errors that in Python would end up being runtime errors actually get caught at compile time in Rust. So this is really cool because you can avoid shipping bugs in the first place, and I think everyone likes that to not have bugs. So this is just one example of where you can kind of see Rust's benefits, and that's in type safety and specifically null safety. So this kind of sets Rust apart from Python and also other languages like Java or C, C++ that you might be familiar with. So let's take this snippet in Python, which you have two variables, A and B. You set A to none, B to 0, and then maybe you have some code where you would expect A would get initialized to some value. But for whatever reason, its value remains none. And so when you try to compare A and B on the last line, of course, we get a runtime error, and that's sad. But in Rust, if you try to write basically an equivalent code snippet, this actually won't compile. And the reason is that in Rust, you can't just set any value to none or null. It has to be explicitly typed as an option value, which you would do like this. And then if even if A doesn't get changed later, actually the compiler won't let you do this comparison because it knows that A might be none and you haven't handled that case properly. So the Rust compiler would force you to write this code instead. And this if statement, all it's doing is making sure that A is not none. And if it's not none, it's going to take out that inner value and use it for the comparison. So in this case, if A is still none when we reach this if statement, we'll just skip over that code completely, and there's no problem. So it works at compile time and at runtime. And this basically leads me to kind of one of the, I think, fundamental philosophical differences between Rust and Python, which is that Rust involves more upfront effort because you're forced to handle all of these cases that you could skip over when you're writing Python. But compared to a language like Python, you have fewer runtime errors. So that brings me to the second topic I want to talk about, which is more generally overviewing Rust's safety and reliability guarantees. So these are really, I think, what make Rust unique compared to a lot of other languages, and especially when compared with a language like Python, which I feel doesn't have so many safety guarantees. And the first thing I want to mention that I really like about Rust is explicit mutability. So by default in Rust, values are immutable, which means that once you set the variable and if you didn't declare it as mutable, basically you can't change it anymore. And so for this, I want to show you this Python snippet where we have a list of numbers and we have a mystery function. We don't know what the mystery function does right now. We don't have access to its implementation. And what we want to know is what is the value of numbers at the end of this code snippet. And it could be anything because we don't know what mystery does. And lists in Python are mutable, so mystery could make arbitrary changes to that list. Might not necessarily be a problem, but this is just how it works in Python. On the other hand, in Rust, if we write this equivalent snippet where we set numbers to this vector, it's called in Rust, of 4 numbers, and then we pass it as a reference, that's what this little and sign means to mystery, we actually know for sure that the value will be unchanged. And that's because, of course, we didn't declare numbers as being mutable. So let's say we did want to give mystery the ability to change numbers. How would we do that? Well, if we want to mutate something in Rust, it has to be declared mutable. And we can declare a variable as mutable by using the mute keyword, which I've done here. So now you might think this code snippet, we don't know what numbers is at the end because mystery could have changed it. But actually you would still be wrong because mystery is getting an immutable reference because we just have the and sign and then numbers, and this means the reference is immutable, and so the function can't modify anything at that memory location. So references also need to be declared mutable explicitly, so it's very clear when your code can change values. If you want to do that, you would basically need to rewrite the code as follows. The key part here is the mut after the ampersand, although I also changed the function name to indicate that you would need a different function signature basically to be able to take a mutable memory reference in the first place. And so this explicit mutability means basically you're not going to get any unexpected changes to variable values. So you could imagine in Python, maybe especially if you're sharing an object across different parts of your code, that some part might make some change when you didn't expect that in another part of your code. So this is enforced in Rust. The next topic I want to mention, and I think Christian also mentioned it in the previous talk, are ownership and borrowing. And this is another unique feature in Rust that allows us to ensure memory safety at compile time without garbage collection. So this is really cool because we can't have memory leaks as easily as in a language like C, but at the same time, we don't have a garbage collector which adds like a performance overhead. So how does this work? And this is maybe one of the more complex subjects in Rust, so I'm going to do my best to give you an overview, but I apologize if it's a bit advanced. I will have references later so you can read afterwards. All right, so ownership. Here I have a little snippet where I've made a variable hello, and I'm assigning it to a string that contains hello world. What you need to understand about this string from is that it's going to allocate an area of memory on the heap to store this string. So if you're familiar with C, it's doing like a malloc basically. And then hello is now the owner of this heap allocation, it's called. Every memory allocation has one owner in Rust. Now we pass hello to foo. And this time you notice there's no ampersand symbol in front of hello. So that means we're transferring ownership of this heap allocation into the foo function. So this then means that foo can do whatever it wants with this memory. It could mutate it. It could do other things. It could pass on ownership to somewhere else. it has total freedom now to do what it wants with this heap allocation. But in order to make sure that we don't leak memory, the Rust compiler, as soon as the single owner goes out of scope, will free that memory allocation. So this code here will fail to compile, and the reason why is that when we call hello and give it, or when we call foo and when we give it ownership of this string allocation, basically at the end of foo, Rust drops it. It frees that memory because the owner is done with it. And so Rust's compiler has something called the borrow checker, which will know that this has gone out of scope and give us a compile error when we try to print hello. So how could you fix this? One way would be to clone that string. So this will create a new memory allocation on the heap with an exact copy of the original string and pass that to foo. So foo can do whatever it wants with it, but we still keep ownership of our copy. Another fix you could do if you don't need like this full access to the memory is you could pass by reference, which in Rust we call borrowing. So now you would again need a different function signature that can accept the borrowed reference instead of the owned data. And so the two function signatures might look like this. And so now I want to give you maybe a little more information about borrowing, because that's also a very interesting subject, because of course we have always one owner in Rust, but then how many borrows can we have at the same time? So of course we already saw both of these examples earlier on the explicit mutability section. In the one case we have an immutable reference, in the other case we have a mutable reference. In both cases, there's only one borrowed reference at a time. And both of this, like this is allowed, it works. What if we want to have multiple borrows, though? In the case of immutable borrows, this is okay, because you could imagine a bunch of people can be reading the same memory, and they won't interfere with each other because nothing gets overwritten. So in this example, I've added the second line, which is going to borrow numbers. It's specifically going to get a reference to the first two elements. It's pointing to the exact same memory as the numbers vector is. And then we're going to use that borrow again on the final print line, where we're going to print just those first two numbers. And then in the middle, we're going to pass a reference of the entire numbers vector into mystery. This is fine because mystery can't do anything unexpected with numbers that would modify the first two numbers in some unexpected way. But as you might be guessing, if we were to have an mutable and an immutable borrow at the same time, this would be a problem. So again, we have the same first two lines, except now numbers is defined as a mutable variable. We have this immutable borrow still of the first two numbers, but in the middle, we're going to try to pass basically a mutable reference to mystery mute. And the compiler won't allow us to do this, of course, because that mystery mute could alter the values in first two numbers, even though that's supposed to be an immutable reference. If that was the only thing that could happen, it wouldn't maybe be that bad. But the other thing that could happen is because this vector is on the heap and it's a resizable data type, we could actually either shrink the vector or grow it so much that we need to reallocate to a new memory slice, and that would invalidate the original reference we have in first two numbers and lead to a segmentation fault when we try to access it on the last line. And so for the second reason, actually, we also can't have multiple simultaneous mutable borrows in Rust. We can always have either just one mutable borrow or as many immutable borrows as we would like. That moves me into the final safety thing I want to talk about, which I don't have an example for. I instead have a happy Rust mascot there. But it's called fearless concurrency. And basically it means that in Rust, the compiler is able to check that anywhere you have some data being shared between threads, that the data types you're using are thread safe. So if your Rust code compiles, it's thread safe. You don't need to worry about anything else if it compiles. And this is like really cool because you can avoid a bunch of concurrency bugs in Rust with this. All right, that brings me to the third topic I want to talk about, which is, I think, a great benefit of Rust, and that's all the tooling around it. So a lot of this tooling, as Christian also mentioned, is bundled into this Cargo command line tool, and so you already have like this one way to access all these tools I'm about to show you. So yeah, it's really cool that you have this ecosystem in Rust, basically. And the first thing I want to talk about are the compiler warnings, because these are very informative and friendly, and they are really a great help when you're just starting to learn Rust. So let's take again this sample I showed you with the immutable and mutable borrow. If we try to compile it, we get this error. And so you can see there's a lot of colors in there to help show where the problem lies. We can see it looks really similar to my slides, actually, because I think I basically based them off of this. But you can see it shows you the immutable borrow. It shows where you use that again. So you can see that it's occurring simultaneously to the mutable borrow. And then that's where it tells you, okay, this is not allowed. You need to fix your code. So Rust compiler is amazing. Next thing I want to mention is the Clippy linter, which is a standardized linter in Rust, and it has standardized default rules. And this is really cool because basically it means that any Rust code you see out there is very likely to have gone through this linter, and so it's very consistent. And the lints are really exhaustive. I think there's like 700 or more lints, of which a decent number are enabled by default. And so here I'm just going to show you a couple of them. So let's say we have this function called isPositive, where we try to detect if a number is greater than 0. If it is, we return true, otherwise return false. Of course, we could just return the Boolean comparison directly, and the linter will complain about this and tell us that we should write this code this way. But actually, this can also be improved. Anyone who knows Rust would know that the return statement is unnecessary. And if we just remove return and the semicolon at the end, this will actually just return that value. And the Clippy linter will tell you that. So even if you're writing Rust for the first time and you don't know about this rule, Clippy will just teach you on the spot, and then you know for next time. There's, as I said, a lot of lints that are enabled by default, but also there's some optional ones which you can enable depending on your needs in the code base. And I have this code base, Sentry CLI, where we've had some new contributors lately, and I've found myself enabling quite a few new lints because I would notice something in code review that's unidiomatic, and I'm like, there might be a lint for that. I check, half the time there is a lint, and I just enable it. And now I don't need to comment in code review and watch for this. I just push it, I update their branch on the new branch, and then their CI fails, and then they need to fix it. No arguments. Frictionless code review. The next really cool thing that also helps in code review is Rust format. So there's standardized formatting for all Rust code. This is also, of course, built in through that Cargo command line, as I mentioned earlier. So we have this very badly formatted function. Rust format will fix it like this. That's cool, but I mean, it's not quite enough to be really special. So I think the special thing is that this is also very opinionated, which means that there's always sort of like a correct way to write any type of Rust code, and this avoids like these ideological arguments of what should we do? And then people just get mad in code review. So like either of these where we have the opening brace on the next line or where we've put all the arguments on the separate lines, in this case, are not the correct format in Rust, and Rust format will just correct them to the correct thing. So you can put this locally in your IDE, you can enforce it in CI, no more arguments, just writing code. Great. Yeah, all of these tools you can have directly in your IDE via Rust Analyzer. So like the compiler warnings and linter warnings will all just show up as you're typing the code, which is really nice. You don't need to run the compiler. You just see it right there. So lastly, I want to tie it back to the original topic, Python. Why should you, as a Python developer, learn Rust? And I think the main reason, both of these languages have their own advantages and disadvantages. And when you know both of them, you can optimize which language you use by use case. So Rust is great for stuff like performance, when you have something that needs to be reliable and ideally without bugs. System programming, these are things you can do very nicely with Rust, but the trade-off is you're going to put in more upfront effort to get these fewer bugs at runtime. Python, on the other hand, Python, on the other hand, potentially you can write it more quickly, but there might be more maintenance effort in the end. However, it's really good for quick iteration, simple scripting, and also the data science libraries are, I think, have an equivalent in Rust. So this is a huge advantage of Python over Rust. Next thing I want to mention is Rust is enforcing a lot of safety concepts. And if you learn Rust through the Rust book, which I'm about to mention, you'll also learn about these safety concepts. And they're good practice in languages like Python as well. And I would even argue that understanding these concepts well is more important when you're writing Python than when you're writing Rust. Because if you write Rust, you have the Rust compiler that will warn you and tell you when you did something wrong. In Python, of course, you don't have this. And that brings me to my final point, which is, even if you're never going to write a line of Rust, I think learning Rust will help you write better Python code. So if I've convinced you, I would recommend learning via the Rust programming language book. People also call it the Rust book. It's the official book, and it's my recommended resource for how you should learn. It's how I learned Rust. And if you scan this QR code, you'll get a link to that book, and you'll also see some other links that are relevant to this presentation, like the slides or my LinkedIn. So scan the QR code and learn Rust. Thank you.